Hi students, in this video we're going to continue our discussion on chapter 2, atoms and elements, but this video is particularly going to focus on the periodic table, its organization, and how we can use its organization to help us know whether we're looking at a metal, non-metal, or metalloid on the periodic table. That will serve us well when we go to chapter 3 and discuss nomenclature, the naming of compounds, because we want to know whether we're naming an ionic compound or a covalent compound, and that depends on whether we're dealing with non-metal, or metal and a non-metal. So I'm going to go ahead and start this video showing the overhead and walking you through the basic organization of the periodic table. So in the periodic table, we can see right off the bat a couple of things that are pretty obvious. One, it's organized in rows and columns. Except for on the periodic table, we're going to define rows as periods. So row 1, right, hydrogen and helium, that would be referred to as period 1. Row 2, or period 2, would be lithium all the way down to neon, and so forth and so forth. But really what we should be thinking about is periods are energy levels. So if we had a simple atomic structure, if we had a nucleus, period 1 would be the first orbit. Period 2 would be the second orbit. Period 3 would be the third orbit. Now that's a crude model, but in the beginning of the semester, that's a nice way to look at it, is that the periods are really energy levels or orbits, and that's because they have a certain distance from the nucleus, the electrons that are in those orbits, and that distance is potential energy. The further away, the more stored potential energy, which we call chemical energy, and that's why I refer to it as an energy level. Now the columns are referred to as groups, and groups are essentially families. They're called families because they behave similarly. So they have similar physical and chemical properties. So the organization of the periodic table started with Mendeleev, or Mendeleev. What he basically did was he observed elements, physical and chemical properties, and at first he kind of lined everything up straight across and collected his information, and he started to notice repeating patterns. And these repeating patterns of physical and chemical properties, he ended up using that and developing what's referred to as periodic law. Now we know a law explains what will happen. So what do I mean by periodic law? What he ended up doing was taking the elements that exhibited similar physical and chemical properties, and instead of doing one long line, he stacked them and organized them based on rows and columns. The ones that exhibited similar physical and chemical properties, he aligned as vertical columns, which, remember, in the previous slide, we called groups. So this would be a group, but I referred to them as families because they behave similarly. And then there were some blank spaces, and what's interesting is the blank spaces that he had left were predicted in the future to have certain physical and chemical properties like melting points, boiling points, densities, and he was very accurate with his predictions. So now we have this big periodic table of elements, and a lot of people get intimidated by it, but in fact, don't be. This is the world's best cheat sheet. You're never going to be expected to memorize this. You're only going to be expected to be able to refer to it and understand it. The reason why I think it's the best cheat sheet is it's kind of already organized. It's got this little staircase here that's separating the elements into 3 classes. So all the ones in light green are nonmetals. So we see that nonmetals are on this upper right side of the periodic table. So nonmetals tend to be gases at room temperature. Some are solids like carbon and sulfur, but if they are solids, They tend to be brittle, soft, and poor conductors. But nonmetals tend to have lower boiling points, lower densities, lower melting points. To the left of this staircase, we see our metals. Now, metals are different than nonmetals, that typically they are found as solids at room temperature. Nonmetals, you can have solid, liquid, and gas, bromine being a liquid. Things like sulfur, carbon are solids, and iodine, but we do know that we have oxygen, nitrogen, those are gases, fluorine, the noble gases. Metals, on the other hand, they tend to be all solids with one exception. Mercury is a liquid. So the only two liquids on the periodic table are bromine and mercury. So that makes it really easy. The majority of these elements are solids with the exception of a few gases, the noble gases, oxygen, fluorine, and chlorine. But to go back to the topic of metals, metals, they're defined based on their physical and chemical properties. They have high boiling points, high melting points. That's why they're found as solids at room temperature. They're good conductors of heat and electricity. That's why we use them in wires and circuits, in frying pans. And then in the middle, in the staircase, we see these metalloids. So metalloids have characteristics that are in between nonmetals and metals. So you might think of a metalloid, they're not a great conductor like a metal, but they're a semiconductor. And remember, Silicon Valley, semiconductors. So this staircase here separates our metals and nonmetals, and the metalloids have characteristics that are in the middle. Now, I do want to show you that hydrogen is a nonmetal, but it's placed over here in group 1 because it has what is referred to as one valence electron, or in its period, there's only one electron in its outer shell. Now, why is it important to understand groups and periods? Well, now if I want to identify an element, I could use period 4, group 2, and I would know that that would be calcium, because that would go down to the 4th row, 1, 2, 3, 4, and I would go to the second column, 1, 2, and I would see calcium is period 4, group 2. So it makes it really easy to find elemental symbols. And I also, if I look back to my previous videos, I see the small number 20 over calcium, which is another way I can find elements by using the atomic number. Because if we remember from prior videos, the periodic table is organized by increasing atomic number, which is the number of protons. So if I have 20 protons, I have to be calcium. And it happens to be placed in group 2A, because it exhibits the characteristics of the alkaline earth metals and that family. So here's the periodic table, and we see, again, the metals separated from the nonmetals. So here are my nonmetals, with the exception of hydrogen. All the metals are to the left of that staircase. But I also see that there are two main groups, really. The main groups being the representative elements and the transition elements. There's also the lanthanide and the actinide series, but in the earlier slide, I was separating what are referred to as the representative elements. So when you hear the topic of octet rule, that's because we're thinking in terms of the representative elements. They tend to follow the octet rule, where in their outer shell, they want to have an octet like the noble gases, which are stable, and we see that they are group 8A. So typically the way you number groups is as you go across left to right, we can number it 1 through 18. Another method is, if it's a representative element, we can use the A. So instead of saying 1 through 18, we go 1, Two, we skip this D block where the transition metals are, and there's 10 of them. So then we go, instead of 13, 3A, instead of 14, 4A, 5A, 6A, 7A, 8A. And that's because group 4A, like carbon, has 4 valence electrons. For the transition metals, we use the nomenclature of B to represent those. What's really important to understand is with the representative elements, there are several groups that we're going to focus on, and we want you to be comfortable with the common names. So group 1A, I use the old school method, are the alkali metals, and the alkali metals all have 1 valence electron. Now, hydrogen is actually not a metal, but it's grouped in 1A because hydrogen has 1 proton and it has 1 electron in its first shell. Lithium, we know its atomic number is 3, but it has 3 electrons. So if I think of lithium, if this was my nucleus, which actually has roughly 4 neutrons and 3 protons, it would have 2 electrons in that first shell. And then in the second shell, it would have 1 electron. That's why it's in period 2, because it has 2 energy levels, 2 periods, and it's in group 1 because it has 1 valence electron. And then sodium, 11, that's because sodium in the first shell would have 2 electrons, in the second shell it would have 8, and then in the third shell it has 1. So that's why it's in period 3, and it's in group 1 because it has 1 valence electron. So if I move one over to 2A, the alkaline earth metals, they're in group 2A because they have 2 valence electrons. They have 2 electrons in their outer shell. So magnesium, oh, well, beryllium. I don't have a periodic table. I made a careless mistake. In beryllium, there are 4. There's an atomic number of 4, and that's because there are 2 electrons in that first period. And then there are 2 electrons in the second period, and that's why it's in group 2, and so on. But that's actually another video, and I'll put that in too. But if we look, what you really need to know is group 1A are your alkali metals, group 2A are your alkaline earth metals, and then group 8A are your noble gases. They have an octet, they're happy and they're satisfied. And group 7A are your halogens. They're 1 away. They have 7 valence electrons from forming an octet. And that's why they're so reactive. And then these have no common names, but they are representative elements. And this block right here is referred to the transition elements. So I hope this video helps you understand the basic organization of the periodic table and realize that you do not need to memorize the location of everything, and you'll be able to refer to the periodic table. So thanks for watching. If you have questions, go ahead and leave them. Thank you.